Hello everyone and welcome to tutorial number 6 of Introduction to Deep Learning. This tutorial is about exercise 6, namely hyperparameter tuning, but first we would like to do a short review of the solution for the past exercise, which we hope you were all able to solve without too many problems, and then we will review the next exercise. So in the last exercise you had to implement the sigmoid activation function. And first, let's have a look again at some activation functions that you saw in the lecture. So there is the sigmoid and there's the ReLU that you had to implement in exercise number 5. And in exercise number 6, you will be implementing the forward and backward passes for tanh and leaky ReLUs. And if we look at what you had to do in exercise 5, so we can, just to frame it mathematically, what we have here is x's, which is your input data of dimension d, and then you have this d plus 1 for the bias trick. Instead of representing the bias as addition, we just add another 1 here, and then the weights here are the bias. And this is written as matrix multiplication, so you have the input x times the weights w, and then you get these scores sigma, which you put through the nonlinear activation function, which is the sigmoid in the case of exercise 5. In practice, what happens is that you don't just do it for one sample, but you have all the samples. You have n samples that are stacked on top of each other. So the input here is a matrix of dimensions n by d plus 1, and then you multiply it by the weights, and then you get, for each sample you basically get one value, but because you have many samples, you have n rows here, then you get, after this matrix multiplication, you get a vector of these n scores, and that's what you input to your sigmoid function here. And it just, for every entry, it returns a number between 0 and 1. And that is your output for each sample here. So you do this for the forward pass, and then you write the derivatives for the backwards pass. And let's see what happens in the forward pass then. So this is the formula for the sigmoid function, which you've all seen already. And just a mathematical fact that this is the derivative of the sigmoid. This is just something you have to write down, do it on paper, and see that you can derive the top here and get to this expression. What's special about it is that the derivative of the sigmoid function can be written in terms of the sigmoid function itself, which is a nice property and saves you some computational power. And that's why it's a good activation function for neural networks, because you only have to evaluate basically the value of the sigmoid, and you already have the value of the gradients for free. Now what happens here is that the sigmoid is a function from R to R. It's a scalar function that takes a number in R and returns another number in R. But as I said earlier, we're vectorizing everything, and we stack all our input samples as rows. So in fact, the input to your sigmoid function is not a number in R, but a vector in Rn. And n is the number of samples here. So what you do, which you probably all intuitively did it anyway, you just apply the sigmoid function for the same sigmoid function to each coordinate of your scores after the matrix multiplication. So we call this here sigmoid tilde, and sigmoid tilde is now a function from Rn to Rn. So looking back again at this slide, we write that this is a vector in Rn and this is a vector in Rn, and now let's see how we do the forward pass of this sigmoid tilde function in the implementation. So here's the piece of the code from the exercise, and this is what you had to implement. So here you see basically exactly the mathematical formulation of the sigmoid function, but remember that x here is not a scalar value, it's a vector. It's a vector with n dimensions, and because it's numpy, then numpy can also handle that and does it coordinate-wise. So basically the exponent here is happening for every coordinate independently. So is the 1 plus, and so is the 1 divided by. So this is doing already the sigmoid for every coordinate. And cache is what we need to memorize for the backwards pass. And in the case of the sigmoid function, since we saw that the derivative can be written in terms of the sigmoid itself, all we have to store is just the output, which is the sigmoid. And that is what we return for the forward function. Now we want to do the backwards pass. So before we look at the code, I would like to do the derivation on paper. So we saw that the sigmoid tilde that we're using is a function from Rn to Rn. And that does it for every coordinate. And as a function from Rn to Rn, the derivative is, of course, a matrix. It's the Jacobian matrix of this function. And you have all these partial derivatives of every coordinate with respect to every variable. But since this operation happens coordinate-wise, it happens that the Jacobian matrix is just a diagonal matrix, because the value of this coordinate, for example, does not depend on x2 or xn. So all these are 0, and this is the Jacobian matrix. So let's see how we take this and integrate it into the code. So here's the backwards function, and this is what you had to implement. And this here is the solution, and let's break it down and see why this is the solution. So what you see here is the cache times 1 minus the cache, and this is basically the derivative of the sigmoid here. Because if you remember, we said just a few slides ago that cache is simply the output of the sigmoid. So sigmoid times 1 minus sigmoid, this is exactly the derivative of the sigmoid. And the out here is the upstream derivative, and we have multiplication between them because of the chain rule. There's a few things that you should notice here that are very important that you don't notice if you just look at the solution, that it just looks trivial. But in practice, I think many of you, when you were implementing this, you had quite a bit of questions or didn't manage to do it very easily from the start. So they are, of course, some differences from what you do on paper and how you implement things in NumPy. So as we said, on paper, the cache, which is the output of the sigmoid, is a vector that has shape n by 1, and the derivative is a matrix n by n, which is the Jacobian, that diagonal matrix that we saw earlier. So we have it here, but in fact, we use in this implementation, we use coordinate-wise multiplication. So the trick is that you take this Jacobian matrix and you say, okay, we don't need all these zeros, all we need is what's on the diagonal here, and we can write the Jacobian as it more efficiently as just the vector that has these values, because matrix multiplication with a diagonal matrix is basically like a coordinate-wise multiplication with whatever you're multiplying it with. So you can write it as a coordinate-wise multiplication of whatever you want with this vector, because this is a vector and the cache is a vector. And of course, these derivatives are just this sigmoid times 1 minus sigmoid of every element, and this is happening here also, coordinate-wise. All right. So now we move on to exercise 6. So a reminder, in the previous exercises 3, 4, and 5, we had to implement the data loader dataset classes, and then you implemented the models and the loss functions, and finally an optimizer so you can train the whole thing. And this exercise is more about the training process and the choice of which hyperparameters you take and how to choose the best model and get the best accuracy score and generalization capabilities of your model. So in exercise 6, you will be using basically all the functionalities that we previously implemented, but this time, in order for everyone to have the exact same starting point, we implemented everything for you. So you will be using basically a reworked version of all the code that you've been writing in the previous exercises. We also provide you some additional functionality that you haven't implemented, and this is stuff that has mostly been covered in the lectures, and the notebooks guide you through these additional functionalities. So by doing this notebook, you will basically be just training networks. It's not about coding this exercise, it's about training many networks and choosing the best one. So we provide you with the data and the networks, and all you have to do is just play around with hyperparameters, train the networks, and see what scores you get, and do that in a smart way such that you're able to exceed the score that's required to pass this exercise on our test set. And the thing is, it's not a very easy task to choose the correct hyperparameters. And that's what this exercise is about. So, as the code for this exercise is different from the code you have written, it is worth taking some time to read the code that we provide you with. It's a bit more modular and has some functionalities, like here you can split the data for train and validation and tests, and you can change this and have a look at all the functions that we provide here. They may be useful for you in the future or during this exercise. Same for data loader, that hasn't changed much. It just iterates over the data and provides it to you. And for the solver, we've also added some functionality. So have a look here as well. And yeah, we provide you this base class classification net. It's very modular. You can just here provide all the hyperparameters that you wanted to run with. And it supports that and does the forward and backward passes for you. And this is a great base class to start with. If you do want to have fancier networks, more customizable, there's an extra class there, and you can build upon it as a template and do whatever you want basically, and maybe you get better accuracy if you really change the architecture a lot. So the data set we work on in this exercise is Cypher 10. You're already familiar with this data set. It has 10 classes and many images that are 32 by 32 pixels. And your task is to predict which of the 10 classes this image belongs to. So previously we've seen the binary cross-entropy loss for tasks of binary classification, where you only have 2 classes. So in this case, this is not binary anymore, as we already said, and you saw that we have this generalization of the binary cross-entropy loss for the multi-class case, which is called the multi-class cross-entropy loss, or the softmax loss. And here you have C classes, and basically your model predicts not a single scalar between 0 and 1, but it predicts basically C scalars that are the probability, each one is the probability that this data point belongs to each respective class. And then you just take the argmax, and that is the class that it belongs to. So you don't have to worry about this for now. This is implemented for you. You just have to focus on the training. And we will talk about this later in the lectures. So what's very important in machine learning is this data split that you start with. So you're usually given a data set, and then you have to wisely use your data both for training your models, but you also want to keep some data aside for validating your models. That is, choosing which of the models you've trained are the best. And you also want to keep data aside for evaluating the final model that you come up with. What's very important, and many people get this wrong, is the test data should only be used once in the end. So you train many models with this training data set, and then you see how each model performs on the validation set. You can use that to know when to stop training it, when it's starting to overfit, or get a general sense of how good this model is at generalizing. But if you then test every model also on the test set, and then choose the best one, you're basically turning your test set into a validation set. So you shouldn't do this. The test set should only be used once at the end of the process, so you get a sense of how well your model actually performs on unseen data. So for this exercise, we provide, you also have your own test set as you split the data, but the test set you will be evaluated on is a different set of images that we keep on our server and you do not have access to. So here you see a split of 60-20-20. Maybe it's not the most common one. Sometimes people train on more of the data set because it's not so easy to get good training data. So you can see sometimes maybe 70 or 80% here and less on the validation and test. So these are the data that you find your hyperparameters on and experiment on. And this you only use in the end of the notebook. And then using this validation set, you can basically tell if your model is underfitting or overfitting. Because if you plot the graphs of the train error and the validation error, and you see that the validation error is still decreasing, as well as the training error, then it means you can keep training your model, and you're not overfitting it. And conversely, you can see that your model is overfitting if the training error keeps going down, but the validation error is remaining constant. So this can help you in the choice of some hyperparameters, for example, the training time you're giving it, or maybe you need a smaller learning rate if your training error is plateauing, for example. So one more important thing is this diagram that you've already seen in the lecture with Professor Niesner. So in the way to read this diagram, you have to replace the word dev dataset with validation dataset here. So this basically lists all the cases. For example, if your training error is quite high, then it means your model might not have enough capacity. So you would consider adding more parameters to your model by, for example, adding neurons or adding more layers to your model. Or maybe you just still have a training error that's high because you're not training long enough. And if your training error is not high, then you ask, is your validation error high, for example, or both of them are high. And this basically lists all the cases and what you should do in these cases. So how do you start with this exercise, or in general, how do you start training neural networks? So the first thing to do that's very important is to just start with a single training sample. You never take your entire data set and try to train a neural network on it first thing. usually you also have bugs, but first you want to see that your network is implemented correctly, and as a sanity check, you just take one image or one data point. It need not be an image, but you take one data point from your data set, and you make sure that your model can overfit and get basically 100% accuracy, because a model should be able to overfit to a single data point and memorize the correct label for it. So once that works, you say, okay, I will now take a bunch of data points and see if my model can still perform reasonably well on this bunch of data points. And if it does, it means your model is probably implemented correctly and you're on the right path. And only when that works, then you take the entire data set and you start training on more and more data. And at some point, when you have enough data, you will start seeing that your model not only memorizes the images that you've been feeding it, but also starts generalizing to unseen data. So if you look at the validation curve, in these steps, the validation curve is probably meaningless because, I mean, when you're training on one data, you have zero generalization. Also, when you're training on 10 or 20 images, then you cannot expect your model to generalize. But once you start training on thousands, your model does not have the capacity anymore to memorize all the data you're providing it, and it will start to have to, let's say, learn something. And that's when things start to work. So, for example, this is what you can expect when looking at training curves for the first step when you just fit one sample. So you see here the training error is constantly decreasing. It means the optimizer is working, it's doing its thing, all the way down to zero basically. And of course the validation error, which is testing the model basically on data that it doesn't train on, is basically starts as random and it either remains very bad or even keeps getting worse. And here you have when you train it with a few samples, and it's very similar. It doesn't go down as smoothly because the problem is less convex, it's harder to optimize, but you still see the same effect basically. So your model is able to overfit and almost get it to zero, and the validation loss keeps going up because it has no generalization capabilities. So what are the hyperparameters we're trying to tune? So for us, it's anything that determines how your model looks, that is its architecture, and anything that determines what the training process looks like. So for example, for the architecture, it can be your number of layers, the number of neurons that you have in every layer. It can be activation functions. It can be regularizations or normalization layers that you put there. It can be the training scheme. It could be, for example, a higher or lower learning rate or learning rate decay, or how long you train it for. And your task in this exercise is basically to try many sets of hyperparameters, train it on your computers, and then submit it to our server once you think you have a good enough model. And then you get feedback from the submission system, and it tells you whether your model is good enough or not on the unseen data. So how do you go about doing this? The first and obvious thing is just a manual search on the hyperparameters. On the one hand, it is naive to think that you can just come up with the right hyperparameters because it is kind of chaotic. You have multiple hyperparameters, and also changing one affects the others as well. But still, we advise you to try starting with this manual search, because you can get a feel about how changing each one affects the model and its training and perhaps the accuracy. And then there's the smarter ways that are automated that you've talked about in the lecture. There's grid search and random search. So we have actually implemented these for you, so you don't have to worry about implementing it. You see this here, and basically you can provide a set here of hyperparameters that you want to try, and basically this script just tries all these combinations, and from this you can take the one that has the best scores on the validation set. You can try, of course, both grid search and random search. One thing is, don't just do it blindly, but think of the effects that changing one thing might have on the other. And also look at the graphs, it's very important, and figure out what's happening. So, for example, how hyperparameters affect each other. If you use a smaller learning rate, it could be that you would have to train it for longer because the steps are smaller. So you'll need more iterations. And also, if your model is overfitting, you might want to regularize the model by giving it less capacity, for example, and having less neurons. One more part of the exercise is the activation functions. We saw this slide in the beginning of the tutorial. So you've already implemented the sigmoid and reduce, but for this exercise, one hyperparameter is actually which activation function you're using in your network. You might want to use leaky reduce. They could increase your performance, or you might want to try out tanh functions. So these are actually not implemented, and if you want to use them, you have to implement them yourself. It is, of course, a great exercise to do it, even if you've passed the accuracy for this submission, but it's optional, it's not graded. As for the submission, everything that you need to do is just train the model and get a performance that's greater than 48% for the submission. This is all you're graded on. If you succeed, then you pass the exercise. If your score is less than 48 on the test data set that's on our server, not on your test data set, then you don't pass the exercise. What's important is that you have in mind that the test data set on the server is slightly different from the one you have on the notebook. And it could be that you get a good score on your notebook, but when you submit it on the server, it's still lower and it's not generalizing well to our test set. So my advice is have a model that performs a little bit better than what it should, than the minimum in your notebooks, and then only submit it. And of course, we have the leaderboard, and this is actually the first exercise where the leaderboard makes sense. So here, it's actually the scores of your colleagues, and you can see how well others have managed to train their models. And yeah, do compete. It's interesting to see how well you can get it done. Last semester, people were quite, they took initiative and did a lot of custom stuff in the networks and got pretty good scores. So, recap and outlook on future exercises. So we had all these exercises we did in NumPy 3, 4, 5, and 6. Now we have the next exercises 7 and 8. So at this point, after this exercise, we will be switching to PyTorch. We will no longer be using the implementations that you wrote or that we wrote for this boilerplate code of training neural networks. We'll be moving to PyTorch that is more efficient and has really nice API, and we will be using it to train our neural networks. So exercise 7 will actually be not a submission, so you could call it optional. This is basically notebook for you to get to know PyTorch and PyTorch Lightning. It is, of course, necessary to do for exercise 8 because exercise 8 uses PyTorch. After exercise 8, the last 3 exercises are about applications of neural networks. So we will be diverting from simple MLPs or networks that are fully connected to different architectures or different concepts in deep learning that are aimed at solving specific tasks. So we will do convolutional neural networks for images, and we will use them to then solve semantic segmentation. And finally, we will do RNNs for time series data. So that was all for today. We remind you to watch lecture 7 on Monday about training neural networks. And then on Wednesday, as usual, at 4 p.m., you have the deadline for exercise 6 that we just presented. And on Thursday, we'll have our next tutorial, number 7, where we introduce PyTorch. So we wish you good luck, and we'll see you next week.